On these next ones, it says determine whether each is odd, even, or neither. Reminder of your rules. If a function is, let's start with even. The function is an even function. That means it has y-axis symmetry, such as y equals x squared. That's your most basic even function. It's symmetrical across the y-axis. Okay? The way that you test to see if something is an even function is if f of x is equal to f of negative x. Such as f of 2 equals f of negative 2. F of 3 would equal f of negative 3. You would have that y-axis symmetry. So there's your test. If you don't remember it, you can write that down again. Your test for odd functions. And again, an odd function is like x to the third. Or actually, just simply y equals x is an odd function. Odd functions have rotational symmetry around the origin. To test to see if something is an odd function, you would test to see if f of negative x is equal to negative f of x. There's your odd function test. Now here we're going to test to see, are these two functions odd functions or even functions? Now one way of doing this, now this is not foolproof, but what I did is I took and graphed, and this is a pretty neat looking graph. You've got an asymptote line here. You've got a growing, it's kind of a growing cosine function. It gets a little bit taller, the amplitude is changing as you go, and then it spins down, and then the same thing over here. First off, let's even look and see, do we think this is an even function? No. If you flip this thing across this y-axis, you don't get the same thing on left side, right side. So it's definitely not an even function, but it could possibly be an odd function. If you spun this around 180 degrees down to here, it looks the same. Now, is this enough to determine, yeah, this is an odd function? No. We actually have to go through the test to just make sure. So let me shrink this back. To determine if this is an odd function, again, this is your test. F of negative x would have to equal negative f of x. First off, let's find f of negative x. And hopefully you're seeing why this is put into the section it's put into. It's because we just went over those identities that told us what to do with cosine of negatives, sines of negatives. So f of negative x would equal the cosine of, instead of 2x, we have 2 times negative x, which is negative 2x. And then in the place of x, we're again going to plug in negative x. Now let's go back and remind you. Here's your identities. Odd and even identities. The sign of a negative, you can bring the negative out front. The tangent of a negative, you can bring the negative out front. But with cosines, you can actually just dump the negatives. The cosine of a negative angle is equal to simply the cosine of that angle. And the reason why, reminder, if you've got a 30-degree angle and you have a negative 30-degree angle, and I ask you to find the cosine of those angles. Cosine, if you were on the unit circle, let's say that this is a radius of 1 and this is a radius of 1, cosine is the x value distance. Whether you're in the first quadrant or the fourth quadrant, do you see both of those values would be positive? So that's the reason if you're doing the cosine of 30 or the cosine of negative 30, it really doesn't matter. You can just dump that negative and find the cosine of positive 30 in its place. So let's go back to our problem. When you're dealing with a cosine of negative, you can simply drop that negative. So the cosine of negative 2x is the same thing as the cosine of 2x, and then you've got negative x on bottom. That's f of negative x. Now to finish our test, now let's do negative f of x. That means simply take your function, make the whole thing negative. So instead of cosine of 2x over x, we have cosine of the negative cosine of 2x over x. And you see here, it doesn't matter if I put the negative on bottom, if I put the negative out front, if I put the negative on top, those are the same thing. That's an odd function. So odd functions would have rotational symmetry. Since this is an odd function, we see why the graph looks the way it does. Why is it nice to know when you have an odd function or even function? One reason is for graphing purposes. We can simply graph everything to the right of the y-axis and then rotate that graph around, and we've got everything to the left as well. The second one, here's the graph. honestly, we don't even have to work this out. If you rotate this around, okay, you don't get the same graph. Looks like the symmetry is somewhere over in here. If you spun it around from here, then you'd get this down here, but as this is sine of t plus cosine of t, you could try to plug it in. You could try to do f of negative x, negative f of x, and all that. You're not going to get odd or even. It's not going to be either. I'll go through and show you just as a reminder. Let's find g of negative t, and that's going to equal the sine of negative t plus the cosine of negative t. The sine of a negative, that negative can be brought out front. That's the negative sine of t. Cosine, you can simply dump the negative plus the cosine of t. That's g of negative t. That is not equal to the original, because the test for even functions is does g of negative x equal g of x? If it's equal to the original, it's an even function. This is not even. Check to see if it's an odd. By now finding negative g of t, and find negative g of t, you just simply make everything negative. Negative sine t minus cosine t. And you see that these are not the same. Therefore, it's not an odd function. It's not an odd function either. So that function is neither even nor odd. On this one, same thing, determine. And again, my advice for you, we won't work through this whole problem. My advice for you is first graph these. Pretty weird looking graph here. Keep in mind that anytime you've got vertical lines on your graph, more than likely it's an asymptote line. This is your actual graph. Looks like, and it's weird, cosecant plus tangent looks like, well, this part kind of looks like the tangent graph, and this part kind of looks like the cosecant graph, and that's exactly what's going on there. So that blue right there is your actual graph. That's what it looks like. Now, if you took and spun this around 180 degrees, well, actually, we can do it like this. It's not going to need. Look what happens. Same graph. Okay. So unfortunately, your paper can't do that. So, you know, it's kind of nice. It allows you to see here, that is definitely, it's going to be an odd function. And you can do the test. You can use your identities, but you do that test, you're going to end up that the f of negative x and negative f of x turns out to be the exact same thing. That's the reason it's an odd function. I think it said even or ago. That's the reason it's an odd function. Proofs. You thought that once you got out of geometry, you were done with proofs forever? No, let's do some proofs. Okay, these proofs are not going to be near as bad as what your geometric proofs are. What I want to show here says show that the sine of 2t equals the 2 times the sine of t is not an identity. Now let me show you how you can disprove an identity. Now this is pretty easy. Disproving an identity is a whole lot easier than proving it. Okay, the sine of 2t equals 2 times the sine of t. The easiest, hands down, the easiest way of proving it is by graphing it. I don't know if you remember from geometry, but in order to disprove something, all you have to come up with is one case to where that is not true. Here you see graphs of the sine of 2t, which is actually the blue graph, and then you have 2 times the sine of t, which is the red graph. And the first thing that jumps out in my mind, the first thing I start thinking about is think about how your transformations work. On the second one, this 2 being multiplied out front, do you remember how that changes your amplitude? It's going to make it twice as tall. Well, there's nothing here that's going to make that graph twice as tall. So you've got this 2 here, that's going to compress it. It's going to make it half as wide. It's going to change the period of the function. So the thought is, for every value of t, for every angle that you can plug into this, is this a true statement? No. And keep in mind what identities are. Sine squared plus cosine squared equals 1. Well, look at this. If I graphed, and this is why I can prove it like this. If I graph, I just want to show you, if I graph sine squared x plus cosine squared x I know that sine squared plus cosine squared equals 1. Well, look when I graph this. I didn't have to graph y equals 1. I know what it looks like. Look what happens when I graph sine squared plus cosine squared. I get a graph of y equals 1. So could we use that to prove as well? Well, not really. Because what if there's some little nod or some little jump in the graph? We know that that's true. But now we can very easily, like I said, we can very easily use it to disprove an identity. If it's true, it would be right on top of each other. It would be left side, right side, same graph, but this one's obviously not true. Here's another one that's obviously not true. Let's try to use the arrow there. There we go. Show that cosine of 3t equals 3 times cosine of t is also not an identity. You see one in bold, you see one in plain. Here's cosine 3t. Here's 3 times the cosine t. That's also not an identity. Okay, it's not true. Now let's get ready to prove that some are true. Okay, let's get ready to do some proofs. Tools we'll need, and this is a lot of things that we'll be doing in the next few slides. And all of these are methods of proof. You don't have to write these down. All of these are methods that we're going to use to help us prove that something is an identity or possibly something's not an identity. And these are going to turn out, like I told you the other day, the whole simplifying thing, they're kind of like puzzles. Okay, it's trying to get from point A to point B, trying to figure out how to do it. And, well, we actually start out with a proof here. It says, verify that the following equation is an identity. We're going to try to prove it. One method of proof, one method of doing this is what I call simplifying the ugly. We're trying to prove that 1 plus secant x sine x tangent of x is equal to secant squared x. Our method of proof is we're going to take the ugly side of that equal sign and try to turn it into the clean side. If this is truly an identity, we should be able to take this and turn it into secant squared x. So what we do is we start with 1 plus secant x times sine x times tangent of x, and we try to turn it into secant squared. We did this the other day. We called it simplifying the other day. I gave you this type problem. I said simplify. The nice thing about proofs is, though, we know what we're trying to simplify it into. Is we're going to try to take this, we're going to try to simplify it into secant squared. You know, we're going to see if we can do that. If we can do it, then this has an identity. The method is take everything that's not sine and cosine and try to turn it into something that is sine and cosine. So I'm going to take 1 plus secant sine tangent and turn that into 1 plus, what is secant? Good. 1 over cosine. Times, we got a sine, leave it as sine. Times, what's tangent? Sine over cosine. Those are your reciprocal identities. Your tangent equals sine over cosine, and cotangent equals cosine over sine, and sine squared plus cosine squared equals 1. Your reciprocals and your Pythagorean identities use a ton. So now we're left with 1 plus. On top we have sine squared over cosine squared. What is sine squared over cosine squared? Tangent squared. Sine over cosine is tangent. So sine times sine over cosine times cosine will be tangent times tangent. 1 plus tangent squared. Now go back and look at your Pythagorean identities. I know the one that sticks out in our mind. We know sine squared plus cosine squared is equal to 1. But don't we have one that relates tangent squared and secant squared? If I divide everything by cosine, check me on this. I believe I would get tangent. Cosine by cosine is 1, and 1 over cosine is secant, right? So isn't tangent squared plus 1 equal to secant squared? So can I go from here, 1 plus tangent squared, and just say, oh, that's secant squared? Check. So therefore, is 1 plus secant times sine times tangent equal to secant squared? Yes, it is. We just proved that idea. Okay. Take what they give you. Take the ugly side of your identity and try to turn it into the clean side. Finished. Any questions about that? Another one says verify that 1 minus secant times cosecant times tangent is equal to negative tangent squared. This is nearly identical to the last problem. We're going to take the ugly side, 1 minus secant times cosecant times tangent. We're going to try to turn that into this. We're going to try to make it equal to that. How about Parker? 1 minus, what's secant equal to? 1 over, what was it? 1 over sine, 1 over cosine, and 1 over tangent. Here's how you remember. Watch this. Every function has a code. And what I mean by that, here's your basic one. Sine, cosine, tangent. Obviously, tangent goes with cotangent. They're reciprocals. And from what I just said, every function has a code. Here is cosine. The one that it pairs with will not be cos something because one of the other is going to be cos something. Sine goes with cosecant. Cosine goes with plane secant. That makes sense? One of the two in all three of these relationships are cos something. Sine with cosecant, cosine with secant, tangent with cotangent. So with that said, Parker, secant goes with 1 over cosine. Good. So we got 1 over cosine. Cosecant is 1 over sine. And tangent is sine over cosine. I told you it's similar to that last one. It's not identical, is it? Sines cancel. And leaves me with 1 minus 1 over cosine squared. And Seth, remind me, what's 1 over cosine? Good, so 1 over cosine squared would be secant squared. And again, the relationship. And I have to do this, guys. I need to memorize them. Sine squared plus cosine squared equals 1. I need a relationship between secants and tangents. So I'm going to turn this into tangents. I'm going to divide everything by, because I know sine over cosine is tangent. So divide everything by cosine squared, that would be tangent squared plus 1 equals secant squared. So 1 minus secant squared. Now, what I'm about to show you, you're going to perform a lot of. I've got this this expression here that involves a 1 and a secant squared. So do this. Take this, let's flip flop this stuff around. We need a positive 1, and we need a negative secant squared. So what I'm going to do, I'm going to move this secant squared over here. You see then you've got a positive 1 and a negative secant squared. But to get that by itself, I'm doing a double flip there. I'm moving tangent squared to the other side. That turns my identity that I know is true into 1 on the left side, negative secant squared on the left side, negative tangent squared on the right side. So since I know this is true, I also know this is true. All I did was use simple algebra to manipulate it. So in the place of 1 minus secant squared, I can put that's equal to negative tan squared x, which is what I was trying to prove. It does equal. Okay, on the next one, we're not proving, but we're talking about a tool that we're going to need to use in our proofs. One thing that you might have to do is sometimes you might have to multiply two polynomials together. And when I say polynomials, I'm not talking about x minus 3 times 2x plus 4. That's what polynomials are. That's a binomial times a binomial, but the binomials that we're going to be multiplying together will now have sines and cosines involved in it. You work it the same way, though. These are conjugates of each other. You have a plus and a minus. Anytime you're dealing with conjugates, you don't have to multiply the inside and outside terms because they're going to cancel anyway. So to multiply 1 plus tan times 1 minus tan, we simply multiply 1 times 1. Minus, because you have a positive times negative, 1 minus tan squared x. Because tangent times tangent is tangent squared. Can we do anything with that? What's your identity that involves tangents, squares, and 1s? Your Pythagorean identity. You read it off to, well, actually, we got it right here, don't we? Tangent squared plus 1 equals secant squared. Is there any way we can turn this into tangent squared plus 1? Can we factor out a negative to turn it into tangent squared plus 1? Because factoring out a negative turns this into tangent squared, wouldn't it? But what would it do to this? It would turn it into minus 1. We need a positive 1, positive tangent squared. There is no way that you can get it there. Okay, you're done. 1 minus tangent squared, that's all you can do. Now, if we could have somehow turned that into tangent squared plus 1, we could have took that out, put in secant squared, but we can't. Second one. To square a binomial, okay, you cannot just square each piece because of this plus sign. If there was no plus sign, sure, just square everything. But in order to square a binomial here, that'd be 2 sine alpha plus 1 times 2 sine alpha plus 1. Same way you did it back in algebra. Multiply your first terms, gives you 4 sine squared alpha. Multiply your first term times your second term. Distributive property, I multiply this times both of them. 2 sine alpha times 1 is 2 sine alpha. We're done with that term. Now distribute your 1. 1 times 2 sine alpha is also 2 sine alpha. And 1 times 1 is 1. Same way back in algebra, most of the time you can usually combine your middle terms. This leaves you with 4 sine squared alpha plus 4 sine alpha plus 1. The same way that you're going to have to multiply, sometimes you might have to factor these. If you need to, if you want to use U substitutions, that's fine. If you don't like secant squared minus tangent squared, and you want to come up here and say, okay, let's let U equal secant, and let's let V equals tangent, and then you're going to factor U squared minus V squared instead. If you'd rather do that and factor with all variables, that's fine. But I'm going to factor as is. Difference of 2 squares. Y'all remember factoring like x squared minus 4. That's difference of squares. Difference of squares always factor into conjugates. So here we have 2 sets of parentheses. Probably need to be a little bit wider. Secant times secant gives me secant squared. And again, x is the argument there. Plus and minus tangent times tangent. I didn't have room for my x. Tangent times tangent gives me tangent squared. So factoring secant squared minus tangent squared equals secant plus tangent, secant minus tangent. You have a trinomial over here. You factor it the same way. Like I said, ignore the sign even being there and treat it like an x. X squared plus x minus 2. Factor it the same way you would factor that. 2 sets of parentheses. Josh, what's the first thing that we put in parentheses? It's not x times x this time, but it's what multiplies you sine squared? Sine and sine. Sine of beta, sine of beta. And then we ask ourselves, what adds to give me, be careful right here, what adds to give you this coefficient, which is 1? And what multiplies to give me negative 2? Somebody help me finish that one. What are those two numbers? Close. Negative 1 and positive 2. Sine of beta plus minus 1, sine of beta plus 2. We're also about to start solving quadratic equations again. But our new quadratic equations will have sine, cosine, and tangent involved. But again, just think how good you're getting at solving quadratic equations. If you can do it when you've got sines and cosines stuck in there, then think about having to solve x squared plus x minus 2 equals 0. It makes that so much easier now. Okay? But that's at the end of the chapter. That's enough of those. That's the same thing. That's quadratic. That would factor into. That's actually a perfect square trinomial. That factor into sine and sine. Adds to give you 4, multiplies to give you 4, will be plus 2 and plus 2. So that'd be sine plus 2 and sine plus 2, or sine plus 2 squared. Back to proving now. When you have two fractions that are equal to each other, you somehow want to make one side. Honestly, you can work with either side here. But you want to somehow make one side equal to the other side. Now, something that I was told in college that still really doesn't make sense, a whole lot of sense to me, something I always wanted to do is say, oh, that's kind of like a proportion. And if I can say that this times this is equal to this times this, then that makes it equal. But they wouldn't let me do that. Because I said, well, you don't know if this is a proportion. You don't know if it's got equality. You don't know if it's those left side and right sides equal. Plus, you don't know if 1 minus sine might be 0 that you multiply by. So they said, no, you've got to turn one side into the other side. You have to make them look the same. Now, let me show you a little trick that helps with this. Keep in mind, sine squared plus cosine squared equals 1. Always keep that in the back of your mind. So what I'm going to do, I'm going to take one side and try to transform it into the other. I usually try to do the one that's got the binomial on bottom. So I'm going to come down here and I'm going to take cosine over 1 minus sine. And look what happens when I do this. I'm going to multiply by the conjugate. It's something you do a lot all through math. When you want to transform something, try multiplying by its conjugate. Look what happens. The top turns into cosine. I'm going to leave it as cosine times 1 plus sine. The bottom, when you multiply conjugates, you simply multiply the first and the last. And that turns into 1 minus sine squared. Well, what does 1 minus sine squared equal? Go over here to what I wrote down. Cosine squared. If I took sine squared and moved it to the right side, it says cosine squared is 1 minus sine squared. So what I can now do is take and turn this into cosine times 1 plus sine over cosine squared. See what happens now? One of my cosines on bottom cancels with this one on top and leaves me with simply 1 cosine on bottom. So I now have 1 plus sine over cosine, which is what I was trying to transform it into. When you're dealing with a binomial on bottom, most of the time, especially when you're dealing with one that involves the number 1, most of the time you can multiply by its conjugate. You can use one of your Pythagorean identities to turn it into something else. Okay, another proof. We're asked to try to prove that cosecant minus sine over sine is equal to cotangent squared. This kind of, I got turning one fraction into 2 fractions using the distributive property, or you can think of it again as taking the ugly side, turning it into the clean side. This is still a proof. We're trying to prove that this identity is true. We're trying to turn this stuff into cotangent squared. Another method that you can use, or strategy that you can use while you're solving these, if you've got 2 terms being divided by a single term, sometimes it's a good idea to split them up and write this as cosecant over sine minus sine over sine. Distributive property. Cosecant, instead of, I'll go ahead and write it again. What is cosecant? 1 over sine over sine. Minus sine over sine is simply 1. 1 over sine over sine. Excuse me. To divide 2 fractions, you flip and multiply. 1 over sine over 1. Flip sine over 1, multiply the 2. What does this whole thing turn into? 1 over sine squared minus 1. What's 1 over sine squared? Oops, not 1. 1 over sine is, say it again, cosecant squared. Anytime you have squared identity, a squared function, and then plus 1, minus 1, there's a good possibility you can use your Pythagorean identities. Which Pythagorean identity, look on your notes, which Pythagorean identity involves cosecant squared? 1 plus cotangent squared equals cosecant squared, right? So cosecant squared minus 1, we've got to manipulate this thing. We'll have to move that over, right? What will cosecant squared minus 1 equal? Cotangent squared. What's that I'm always trying to prove? Equals cotangent squared. Make sense? Okay. Now let's work it backwards. What if you have 2 fractions? Let me show you how to combine it into 1. We've done this. We've done this all year. You've got the ugly side over here, and we're going to somehow try to turn this into the clean side. The way that we do that, we're going to try to combine 2 fractions into 1. We're going to find a common denominator. We're going to add them together. So let's start with our whole 1 over cosecant minus 1 minus 1 over cosecant plus 1. Common denominator. What are we going to multiply top and bottom by here? Good. Cosecant plus 1. cosecant plus 1. And we're multiplying top and bottom here by, good. And we know what's going to happen here. When we multiply these two conjugates, I'm going to have cosecant squared minus 1. And again, that looks Pythagorean, doesn't it? Anytime you got that 1 and something squared, that's Pythagorean. So on top, I now have cosecant plus 1. Now careful, you're not distributing 1 here, you're distributing negative 1. So cosecant plus 1, and that'd be minus cosecant also plus 1 over cosecant squared minus 1. Is that not the same identity we used on that last one? Cosecant squared minus 1, yeah. See, 1 plus cotangent squared equals cosecant squared. Isn't that right? So cosecant squared minus 1 will equal cotangent squared, right? Mark it out, mark it out. I'm left with 2 on top. Cosecant squared minus 1, move that 1 over, manipulate it. Cosecant squared minus 1 is equal to cotangent squared. Now let me show you a trick. Let's come down here, scroll down. 1 over tangent. We know the tangent sine over cosine. That'd be 1 over sine over cosine. To divide, you flip and multiply. When you do, you end up with cosine over sine, which is cotangent. You know what this reminds me of? How do you move a negative exponent from the bottom to the top? Make it positive, right? How do you move a tangent from the bottom to the top? You make it, if it's positive, you make it negative. If it's negative, you make it positive. You raise it to the negative 1 power. If it's tangent to the first, it'd be tangent to the negative 1 on top, right? If it's cosecant, then it would be cosecant to the negative 1. Well, raising something to the negative 1 power. What is tangent to the negative 1? It's cotangent. Because when you raise something to the negative power, don't you flip it? And when you take tangent, which is sine over cosine, and you flip it, it turns into cotangent. If you have cosine and you flip it, it turns into secant. If you have sine and you flip it, it turns into cosecant, and so on and so forth. So really, if you want to move tangent from the bottom of a fraction to the top of a fraction, you need to turn it into cotangent. If you had a sine down here and you moved it to the top, you would turn it into a cosecant, and so on and so forth. That's odd, isn't it? But there is a major relationship between those two with the process that you're doing. So let's go back up here. 2 over cotangent squared. Move that to the top. That'd be 2 times tangent squared, which is what you're trying to prove. That stuff is equal to 2 times tangent squared.